All right, good afternoon, everyone. My name is Malavika, and I work at the Institute of Biomedical Engineering in the Department of Engineering Science. My background personally is as a material scientist, but engineering science is very broad. It has lots of different applications, including biomedical engineering and including civil engineering, as one of you has already pointed out. So despite millennia of technological advancements, today the function of things like wood and bone actually remain unmatched. Now, why is that? It's a bit of a mystery. We've made so many different man-made materials. We've tried so hard to be the best, the strongest materials that we can put out there. But for some reason, we still can't quite replace the original biological materials. So today, we're going to try and look at how we can build better implants. But to do that, we need to answer a few questions first. Firstly, what are we trying to replace? So, as you might have understood from the name of the department, it's engineering science. So in order to build better solutions, we need to first understand how the existing solutions work and what we can do to change them. So what are we trying to replace? So let's think about the most common type of implant that we'd put in our body. So this would be something, say, like a hip implant. So there we're trying to replace a lot of structures that help you move. Now, the key component of this is proteins. Now, proteins, you might have come across them in many different forms, but the one thing that's true about all of them is that they help something move in the body. Now, whether that's hemoglobin that moves oxygen around the body, or whether that's collagen, a long, strong structural protein that helps us move our bones and muscles. The function of these proteins is basically to move things. Now, proteins are quite interesting, as are most things in the body, in that they have what's known as a hierarchical structure. So what that means is that they've got a structure of the very simplest molecular form that builds and builds and builds on top of it to create these very different tissues. So we tend to give them certain categories and qualifications. So there's the primary, secondary, tertiary, quaternary, sometimes there's also quinary structures. So the primary structure is talking about the basic molecular building blocks of a protein. So amino acids, what kind of amino acids would you link together to make a protein? There's only 21 different types of these initial building blocks, and yet there are so many different proteins that we create in our body. So just by changing around the order of these, we can create vastly different properties. But it's not just that. After you've got a particular sequence of amino acids, the way in which it coils and uncoils or folds, so that's the secondary structure, will also give it some of its properties. And we'll look at a couple of examples of this in due course. Then these proteins, these little coils and sheets or random blobs, quite literally, can also create larger structures. And that comes together as the tertiary or quaternary structures. So hemoglobin, for example, involves 4 different subunits that's linked together. So that would be a larger structure that we're looking at. So the important thing to realize is that all proteins have this hierarchical structure, and there is an element of building upon different layers that we need to take into account. So we're going to start with a very simple, basic, everyday example, which is keratin, which is part of something very common, like hair, or moustaches if you have them, the horns and hoofs of goats and rhinos. So what is its purpose? What is its structural and biological purpose? Well, keratin actually comes in 2 different forms. In the 3 examples I've given here, it comes in a secondary structure known as an alpha helix. So the alpha helix is the one on the left. Under certain circumstances, it can undergo a transformation, so it can change its shape to create this folded beta sheet structure instead. Now, why is that useful? Well, let's have a look at a graph to see why that may be. So this is a stress-strain graph. How many of you are familiar with this? You might have seen it as a force extension graph as well. Yeah? So Hooke's law. So that's when you have a spring, you stretch it, you get a straight line. That's linear, right? So that part we should expect. Straight line. So far, so good. That's how keratin behaves as well, up to a point. After a certain point, you get something known as plastic deformation. So this is irreversible change. So unlike a spring, it can't change anymore. So what this ends up doing is it kind of has a little plateau, and then you can recover the original strain. Now, why is this useful? Why am I talking about this at all? Well, how many of you have had the misfortune of accidentally jamming your fingers in a door? Quite a lot, I imagine, yes. But there's a reason why jamming your finger in a door doesn't immediately splinter your nail and break it off. It's because there's a process by which that energy can be dissipated. So instead of it entirely splitting those keratin, it undergoes this transformation. So it undergoes an alpha to beta transition here, dissipating all this energy here. And that is a mechanism of toughening these proteins. So by looking at how these structures can interact with each other, we're starting to see how some of these things have biological purposes. So sure, the nail is a fairly simple example, but we can also think about it in terms of the goats and the rhinos, where they might get into fights with others, and they might be enduring really hard, tough environments. And there they need to constantly make sure that a simple little, simple ramming into a tree doesn't cause them to have their entire horn ripped off. So it needs to have some sort of toughening mechanism, some mechanism of dissipating that impact. So that's all well and good. I've shown you an example of how keratin works. This is also true for a lot of materials, but this is how it exactly works for alpha keratin. But let's start to think about another example of this. So what we do know is that if we actually extend this line, so we've only got it up to that line earlier, and we kind of dropped it, so we were able to recover it. But anyone who's pulled at their hair probably knows that at some point it will break. Anyone who's ripped their nail will know that it doesn't just keep extending, it will break. And so that's the little break point that we have there. So if you extend it far enough, it will break. But those of you who've ever tried to brush your hair in the morning after a shower will know that your hair, which is made of keratin, will behave differently depending on whether it's dry or whether it's wet. So all of these proteins will have some dependence on the local environment as well, so the humidity. A good example of this is we can draw the curve at 100%, so 0% humidity, so there's no water at all. So here it behaves quite a lot like a spring. It's just very stiff, so the curve is very steep, and there's a tiny bit of transformation that can happen, but then it breaks. So there's not very much you can do after that point. As you increase the humidity, you're increasing this region where you can allow this transformation to happen. But you can also see it gets less stiff, so the gradient is going further down. So we can draw a couple more curves going from 100% to 0%, or 0% to 100%. And what we see is that as we increase the humidity, so this is this line over here, we have lots of water packing around the keratin, so it's very pliable, we can stretch it out. But it also it has a very low elastic modulus. So something that is not very stiff, but allows you to withstand quite a lot of strain. Now this graph, strangely enough, is actually the basis for most of hairstyling. You wet your hair, you allow it to change shape, and then you dry it so that it's fixed in that shape. It's a very simple principle, but it applies to your everyday situation as well. Now, of course, why does that happen? There must be a reason for it. Keratin has these molecules, these alpha coils, that have two bonds between them. So this is now looking at how the secondary structure is built into a tertiary structure. Some of these are crosslinks known as disulfide bonds, so that's the two little S's over there. And some of these are hydrogen bonds. Now the hydrogen bonds are very easy to break if you incorporate water in them. So have a little bit of water come in there, they break easily, and then you can change how they pack and stack. Now what's difficult is changing these disulfide bonds, and that's where the expensive chemical treatments come in that you probably go, if you do go into the salon for. Those are what's broken when you get permanent changes. That's just a simple example, just a nice introduction into how these proteins work with a simple case. Now let's start to think about something a little bit more complex. Now collagen, I'm a little bit biased because I work with collagen, is one of my favorite proteins because it is ubiquitous. It is found in pretty much every single tissue you can think of. So bone, the cornea, heart, muscles, lungs. But obviously the skin, the bone, the cornea, they don't quite behave the same. They're very different properties. They do very different things. And part of the reason is because of its tertiary or quaternary structure. So how a simple molecule of collagen, which is actually just one of these triple helices, it packs into these fibrils, but how they then pack and stack changes how it then behaves in these tissues. So as an example, I'm going to show you two images of collagen structure. So the one on the left is skin, and the one on the right is tendon. Now, can you start to see why there's a bit of a difference between how they behave? If not, don't worry, I'll give you the answer. So on the left, we have collagen fibers that are randomly stacked. So we've got lots of random fibers, which means that you can literally push your skin in any direction in that plane, and it can withstand those forces pretty easily. But it's not super, super strong in any one direction. On the other hand, in the tendon and the ligaments, you've got it all aligned along a single direction. So along that one direction, it is extremely stiff, extremely resistant to any forces that we put in there. But as soon as you have a little bit of a twist, that's when you start having your ACL tears. So for their purposes, they're actually very well designed. You have got very different structures. So these are looking at the tertiary structures. And you can get lots of different properties in terms of their mechanical properties just by changing how they're packed and stacked. Of course, there will be small changes as well in the primary structure, so say what exact amino acids and what exact proportions of them there are in order to help with some of these differences. But fundamentally, we can pick these apart as independent features. Okay, so I've talked a lot about collagen, but let's talk about bone now. Bone is what I'd like to call a biocomposite. It is 70% biomass crystal known as apatite, and the rest of the 30% is collagen. In terms of volume, it's about 50-50. Now, bone has a very interesting structure because it builds on quite a lot of what we saw. We take that small collagen molecule, stack it into a fibril, stack it into a bundle, make lamella or sheets that are concentric, and then have little channels go through them where the cells actually, so the way I've said it, it's almost as if I'm engineering the bone to have these concentric circles, but of course in the body it's the cells that are producing these layers. So the cells are on the inside producing these layers on the outside. But you can see it's a very complex structure. And then somewhere in here along the collagen fibril is where these apatite crystals sit. So they sit between some of those gaps that I showed you earlier. So what those gaps allowed you to do previously was to have a bit of flexibility. So your tendons, your skin has that flexibility. As soon as you put this crystal in there, it's a bit stiffer. So you can actually withstand, well, your body weight with the addition of these crystals. But hopefully, as most of you might know, if you've ever worked with any sort of crystalline materials, and now that doesn't have to be particularly complex, it's sugar and salt, you should know that they're very easy to grind down. So as soon as it breaks, it shatters. It doesn't just kind of ooze into place. So we don't want that to happen. We don't want, to put just a little bit too much pressure onto our bones and for it to just completely shatter. Having the mixture of this hydroxyapatite or like crystal and collagen allows us to have the best of both worlds. So it allows us to have a little bit of that flexibility that's needed, that resilience, that toughness, while still maintaining the strength and the stiffness that you need from this crystal. So we've talked a little bit about the structure of bone, so we know what the case is within the body, how it works, how it's all arranged to give it its structural function. What's the current solution? So what are we currently doing to replace it when things go wrong? Well, to introduce this first, we'd like to talk about the class of biomedical materials. And when we think about trying to replace, say, our bone with man-made materials, or even other biological materials, there are a few things we need to think of. Is it bioinert? So is it something that just sits in the body and does nothing? Now, in reality, there is no such thing as bioinert. How many of you have had a splinter? Yeah. So that's technically bioinert in that you can get something in there. It doesn't do anything, but what forms is this little capsule around it that over time the splinter becomes easier to remove because it's just isolated this implant that you've put in. So that's bioinert. You can have something that's bioactive. So that's something that helps cells to produce more of the original tissue or integrate within the implant. Or you can have something that's toxic, which isn't always bad. Sometimes you want to kill cells, for example, if you want an antimicrobial coating. Another consideration is the possibility of having something that's bioresorbable. So I imagine this is far more common if you've had stitches recently than in the past. The sutures that are used now, they dissolve over time rather than having to go in again to remove them. So bioresorbable is something that, it helps, it prevents that second surgical step or second intervention. So it can make things a bit easier. Okay, so we've come up with these different classifications, and these are the different general considerations we need to think about when thinking about biomedical materials. So let's look at artificial hip replacement. So there are three components to this, but we'll just focus on the two parts for now. So there's the femoral head, which is basically in the ball and socket joint, it's the ball. And we have the stem, which is essentially this part, the part that's going directly into the bone. So there's two different structural functions that we need to think about here. One is, how do we get that rotation and that well-lubricated joint that we do with just the ball and socket joint with man-made materials? And how do we make sure that we can actually have the same toughness and stiffness and all those wonderful properties that we talked about for bone with this femoral stem? So there are a few things we can think about, so a few considerations, so to speak. We need to match the stiffness to the femur of the femoral stem, and we need to match the toughness to the femur. So what this means is stiffness is how resistant it is to force, toughness is how resistant it is to cracking and falling apart. So common materials that we use are steel and titanium. Steel and titanium have a stiffness of about 200 gigapascals, so it's definitely much higher, and 100 gigapascals. Bone is only 17 gigapascals. Now you might be thinking, that's great, we've got something that's much stiffer than bone, job done. But actually, not quite. Do you know what happens to astronauts when they go into space? They come back and they have a lower bone density because they've been in a low gravity environment. So your bone is not just some material, it's a biologically produced responsive material. It responds to the environment around it. So if we're putting something like steel or titanium in our bone, what it does is it takes up most of the load that you put into it, which means that the bone surrounding the hip replacement actually gets very little stimulation, mechanical stimulation at all. So it starts to resorb. Just like the astronauts, it starts to go away. And that's why you get some issues called aseptic loosening. So you start to get little issues with the matching around that interface. So actually this isn't that great. We want to try and make it as close to this as possible. There are ways around this, so you can engineer different shapes. You can cut out little holes in the material. It doesn't have to be a whole block. So you can try and reduce the stiffness that way. But we will also consider some other solutions maybe in the next section. So let's also think about the ball and cup. So this is a very different issue. So here what we're trying to think about is trying to match what's known as the wear rates to the femur. So now osteoarthritis is something that happens when you slowly wear away your cartilage. That's something that we want to try and avoid with these hip replacements because there's nothing there to repair it. Once we put it in there with synthetic materials, that's it, it's done. So we need to try and match the wear rates to what's organically there. And what we see is that there are different options that are commercially and clinically available. There's the metal on polymer, less good because you start to get little chunks of polymer and the cells don't particularly like that. Metal on metal, a little bit better, even though the sound of metal on metal might be quite jarring, it's actually not so bad. But the best option is ceramic on ceramic in terms of wear rate. Of course, I'm saying this, but if you've ever dealt with a ceramic plate, once it shatters, and you don't want that to happen to your hip. So you need to start to think about how all of these different considerations can be brought in together to create your implants. So that's where we currently stand, sadly. But are there any emerging alternatives? Now, of course, there's lots we can do with these implants themselves to try and make them bond better to the body and try and make them better matched. But there are also completely different strategies you could adopt. And one of them is to look at tissue engineering scaffolds. So this is where you try to, well, we did start the whole session saying the best thing to replace bone is probably bone itself. So why not try and recreate that? So to create tissue engineering scaffolds, so a scaffold, I'm sure most of you must be familiar with it. It's just these large structures you might have seen on the side of a building. So you've got people repairing the building while it's there, but then it goes down once the construction's done. In the same way, here, the construction workers are the cells, and we instead have a temporary structure that's made out of some polymer or something that degrades in the body. So here is where that consideration of something that's dissolvable, biodegradable comes back in. We want something that's temporary so that the cells can use it as a little structure to lay down healthy tissue. We need it to be compatible with the local biochemistry. So we've so far only talked about all of the mechanics and the physical side of things. And we still won't really talk about it right now because it's a very interdisciplinary area, and I'm sure that many engineers probably would like to collaborate with others who have information about this rather than go into it themselves. But it is a consideration to make nonetheless. And we need to mimic the structure and properties of the original tissue. Now, this is across all the different types of properties we can think of. As close as possible, we need to mimic the rates of degradation, the rates of the mechanical strength and stiffness, and of course, the biological response to it as well. Okay, so with these three considerations, I'm going to show you one strategy to make these structures. So if we need cells to go through these structures to lay down new tissue, they need to be a bit like a sponge, they need to be porous. So what better solution to start with than maybe what makes most of our body itself, collagen. So we can start with a phase diagram of water to try and create a collagen sponge. So we start with essentially beef and vinegar, so collagen in acetic acid. We blend it all together and then we freeze it. So we take it into the solid form. So when we freeze it, what happens is we form these ice crystals. Ice crystals are very interesting because water can dissolve a lot of solutes in them. So we have sugar, water, all sorts of things. But ice actually is very intolerant of solutes in its crystal structure. So all of the collagen and all the other things that we've put in there get pushed to the side of the growing crystals, which means that we actually are creating a mold for where the pores will be. So we've got our ice. Our ice is templating these pores in the structure. We now need a way of getting rid of it. If we just turn it back into liquid, we'll just get that suspension again. So we need some way of getting that ice and turning it into gas. And we can do that with sublimation. So we drop the pressure, we allow the ice to sublime, and we're left with a porous sponge of collagen, essentially. So we're recreating the structures we expect to get in the body, but using other techniques like ice templating. Now, of course, there's lots of engineering to be done here, depending on the thermal gradients, depending on the solute environments, depending on the molds you use. You get different shapes of ice crystals, which means you get different pores, different channels, different connectivities. And these are all considerations to make when creating these structures. And you can see some examples of these in real life as well. So these are both collagen scaffolds. These were made at the same temperature, but different solute environments. So this is with some salt, and this is with no salt. And you start to get very different structures. Almost, not quite, but starting to mimic some of the features that we'd seen earlier with different tissues. Now, of course, there are other strategies as well that are emerging. So there's bioprinting of tissues. So this is an example where people are starting to put in all of these different structural materials like collagen and others, but with cells, the cells that originally come from these various tissues, in order to create a variety of different organs. Now we're quite a while away from there. We can create maybe small things. Printing a piece of paper takes a long time. Imagine how long it takes to print an organ. So it's not that quick, but we're getting closer and closer each day. So the question that I now have to ask is really, what would the future look like? And that's where you guys come in. So hopefully you guys, with all the information that you've been given through all of these lectures and otherwise, can find the solutions of tomorrow, and working either with this or just on your own. And this isn't just true for biomedical engineering, it's also true across the board for any field that you choose to go into. That's it. Thank you very much for listening, and I hope you learned something interesting today.